Good afternoon. Welcome to Soils Under Roads and Streets. The webinar will start in about 3 minutes at 2 o'clock. Welcome to Soils Under Roads and Streets. We'll be starting up in about 2 minutes. And for those who are on Facebook Live, welcome. We'll be starting up in about 1 minute for the webinar on Soils Under Roads and Streets, both on Zoom and on Facebook Live. So good afternoon and welcome to our afternoon webinar on Soils Under Roads and Streets. And I want to thank you for joining us both on Zoom and on Facebook Live. My name is David Orr. I'm the director here at the Cornell Local Roads program. Our webinar today is going to be taught by Willie Grimke, one of our circuit riders. But prior to joining us as a circuit rider, and also still now, he's an engineering consultant with over 30 years of experience, and he worked for 13 years in Washington County as the highway superintendent. And so with that, Willie, I'm going to let you get started, and I'm going to turn my screen off so that they watch your lovely face. Thanks very much.
Well, that's a pretty scary thought, but thank you, Dave. So this afternoon, we're going to talk about soils under roads and streets. What can I say? It's a big issue because those soils are what's supporting our pavements. Okay, why does it matter? Just by a show of hands, have any of the attendees dealt with pavements that have started to fail and it was due to what was supporting it?
And if you don't know how to do that, drag your mouse to the bottom. You'll see a place of participant list, and you can raise your hand down at the bottom.
Okay, and I see a lot of hands up, and I see one of the hands is Bill Lamy, who was my counterpart in a neighboring county while I was serving in county government. And I'm sure he has all kinds of horror stories about failing pavements and bad soils, because in our part of the world, one of the things we were blessed with was the Champlain clay. And it's a tough material to build roads on. Okay. I probably asked too soon. For navigation, there is a raise hand pod, so if you need to raise your hand, hopefully I will recognize it and can call on you if you have questions. There's a Q&A pod, and if you open that, you can ask questions, and I'll try and monitor that and respond appropriately. And through the course of this, we will have some poll questions coming up. So if you, and you click what you want, and then we'll show the results of the poll. Okay, here comes the first poll question. What is your primary job function? Are you a highway maintenance worker, highway maintenance supervisor, engineer, or you do something else? So click on the slide or click on the choice, and then we'll see who we've got here.
They don't want to get to 75% for you there, Willie.
Well,
here we go.
Okay. Well, we've got a couple of maintenance workers. We've got some maintenance supervisors. We've got engineers. So this could be interesting, and hopefully you all won't launch hardball questions at me. Okay. So we're going to start out with where we are with our road. Up on the surface that we drive on, we've got our pavement. Then below that, we have a base course. Often it's an asphalt stabilized base course, but sometimes it's stone. Then below that, we'll have a sub-base course, which is often a crushed stone material or a bank run gravel material. And then down here below that, we have our subgrade, which is our native soil, or it's an embankment that we've constructed. And that's a lot of what we're going to be concerned about today, although we will talk a little bit about bases, sub-bases, and surface courses. So just so everybody's on the same page, when a vehicle drives down the road, it imparts load on the pavement, and depending on the thickness of the pavement depends on how much it distributes that load to the various layers below, be that asphalt, base, sub-base, and then ultimately the subgrade below it. So I'll show a slide later which demonstrates what happens when vehicle loads travel on soils without that pavement or thickness separation. And what happens as the wheels progress along the road is it will deflect the pavement, particularly with asphalt pavements, which are flexible by design. And when anything flexes or is a moment's put on it, you tend to get this pattern where it deflects down in a smiley face type manner, and you get compression at the top surface, but you get tension at the bottom. And as many of us know, asphalt pavement is not stellar in tension. So what we want to do, or what we want to have below, is subgrade, subbase, base courses that support the pavement and minimize the amount of flexing so you're not putting it in a lot of tension. And the photos here we've got poorly supported pavement that's starting to alligator crack. Here we've got pavement that's alligator cracking, and here we've got pavement that's alligator cracking. Largely because there's a loss of support of that pavement from below. So one of the things we're emphasizing here is we want to build our roads on a firm foundation. This particular photo was taken in California after an earthquake, so it's an extreme case, but I'm sure many of us who have been in the road stewardship business have seen pavements in, like we saw in the prior slide, that are not built on a firm foundation and begin to fail otherwise. And this is one of the things that can happen when you drive out onto poor soils, even with a low ground pressure excavator. Okay, so our subgrade, what we're looking for with our soils, and what we have and how it's characterized. Gravel, it's in the size range from 1/16 of an inch up to 3 inches. You know, it's good size material. We have sand, which is from 3/100 of an inch up to 1/16 of an inch. And we have silts and clays, which are particles that are smaller than 3/100 of an inch, and silts and clays behave a little bit differently. Now, what we have down below here is gravel. When I was in county government, the town highway superintendents would come to me and say, hey, we're going to resurface our road, or we're going to do some road work. And the farmer down the road has a bank of good gravel that we can use. And they would be referring to the blend of size fractions that had gravel sized particles, as opposed to gravel in the soil sense, which is the 1/16 of an inch to 3 inch size only. So if we're doing base and surface courses, what we're looking for are blended materials that are between 50 to 70% gravel, 25 to 40% sand, and a low percentage of fines. We want 50 to 70% gravel because those particles are big and chunky, and they will help support and distribute the weight. We want the sand to fill in between those voids in the gravel, and some fines in surface course, and it's not as necessary in a base course. We want fewer fines in the base because we want it to be permeable and we want water to flow through it. Where with a surface course, we want some fines to bind that all together. So when we're driving down the road, it tends not to washboard. The stones and sand don't tend to come apart. It all stays more or less stuck together. Just show of hands, has anybody driven down a gravel surfaced road and had it seem nice and firm and hard, almost like it was paved? This typically doesn't happen in March or April, but sometimes in August it will be like that. Okay, yeah, collectively the group has. And that's because that gravel road did have enough fines in it to keep everything held together. And as it dried out in the summer, it tightened up and it was nice and hard. Okay, here's a size chart which shows what we're looking for as percent sands, clay, silts and clays, and gravels for surfaces and bases. So here's the silt and clay line. We want to stay under 15% for both cases, and typically under 8 or 10 for bases to keep them permeable. So we don't want a lot of fines in there. However, here's the gravel, and we typically are looking for, 50 or 60 to 70% gravel for bases, and 50 to 65% gravel for surface courses, and then sand in both cases we're in the 25 to 40%. And that gives us our best probability for having good results. As anybody who's dealt with soils will tell you, there aren't any guarantees, and what we're just trying to do is maximize our probability for success. So one of the things we can do in the field is visually identify what kind of soils we're dealing with. If you have gravels, you can look at it, 3 inches to 1/10 of an inch. Sands, 1/10 down to invisible particles. And then silts and clays. Does anybody know how to determine whether you've got silt or clay? If you do, you're welcome to type into the Q&A pod. And we'll see who the winner is. Because when you're dealing with Caroline, Gary, roll it in a ball or ribbon hand test. You roll it into a little snake and see if it holds together. If it holds together, it's typically clay. If it falls apart, it typically isn't. And then Gary says run a gradation or plasticity index test, which is the right way to do it. Although some of us don't always have that equipment or time at our disposal when we're looking at stuff, trying to make judgments in the field. And down here we have other stuff listed, which really isn't that great for road construction, and that would be organics. And with the note below, soils are mixtures of gravel, clay, silt, sand. So, moving on, how does this affect our pavement? Or what characteristics of soil are we looking for under our pavement? Permeability being one of them. How much does the water flow through it? Is it free draining? Capillarity. Are the voids between the soil particles so small that it will pull water up? Frost susceptibility, which we'll go into in a little more detail, is the difference. It is a combination of capillarity and permeability. Stability. Can you drive on it? Or is it like that first photo at the beginning where it's unstable and you get ruts? Will it compact? Can you get a nice dense soil that will support vehicles? And moisture content, which has to do a lot with compaction. How much moisture is in it in its natural state, and will that allow us to compact? Okay, talk first about permeability, and you can see we're all over the park. Gravel can be up to 30,000 feet a day. Water will migrate, 6 miles a day through gravel. about 1/10 of that through sand. And that's one of the reasons those of you that have any exposure to water and wastewater treatment, we use sands as filters. Silt, not so much, down to 3 feet a day, a little bit of flow, but not too much. And clays, very little. Many years ago, Washington County owned a landfill site jointly with Warren County, and it was all clay because we didn't want leachate going into the groundwater. So clay does not, water will not go through that. Now, capillary rise. Because of the small particles and the voids in between those particles, how high will water get sucked up? With even small gravel, it's very little because the voids are big. With coarse sand, it can come up to 6 inches. And we do a demonstration in the instructor-led doing local roads and streets done right, where we demo capillarity in sand, and we pour it in a basically test tube, and you can see the wet line rising about 6 inches through the course of the class. Fine sand even higher, and then silts and clays are substantial. You can be several feet above the water table and still have water and wet soils because of the capillarity. So, poll question. Which soil has the highest permeability? All right, when we have answers, we'll see how everybody's doing.
Not quite the 75% there, Willie. We're getting there.
Okay.
Well, we'll give them another 10, 15 seconds, and then we'll go ahead
All
and show
right.
the votes. But yeah, that's anonymous, folks. We aren't. We just want your guess here. No big deal.
Yeah, we're not gonna.
Here we go.
Okay. Gravels have the highest. 76% say gravels have the highest permeability, which is the correct answer. And the clays typically have low permeability, which is why we use them for landfill caps and making pots and mugs and flare it. Sands have some permeability because we use them as filters. And silts are kind of in between these sands and clays. Okay, so we'll move on here. Now, we're in New York, and with the exception of Long Island, which doesn't have soils that are super conducive to frost susceptibility, and they don't get as much in the way of freezing temperatures, the rest of us do. So that's something we are very concerned about with our pavements, particularly in the Adirondacks, in the North Country where it gets really cold. So for frost susceptibility, we need 3 features to have a problem. We need a frost susceptible material, something that is likely to perform poorly when it gets cold and wet. We need the cold, we need freezing temperatures, and we need available water to make it wet. And if you noticed from the prior slides, silty soils are that sweet spot with permeability. It'll draw a little bit of water, and capillarity, which will draw it up. And that's what gives us the problems with frost heave in silts. In sands, there's a lot of permeability, but not much capillarity. So unless you're right at the water table, you're less likely to have issues with those. And with the clays, it'll draw it up a lot, but because of the low permeability, it can't draw water up fast enough to build ice lenses, which is what we'll see a little bit later. Now, here in the photo, we see frost heaves sign. And we can surmise that due to the snowbanks on both sides of the road, that we have freezing temperatures. And looking at the wooded areas on both sides of the road and the way it breaks away, I suspect that's relatively wet, which explains why we have frost heaves. So what happens is our pavements freeze from the top down. The freezing temperatures are up above, the earth below is a little bit warmer, and the freezing front migrates down. And as that's happening, depending on the distance from the water table and the capillarity of the soil, it will pull water up. And as that freezing front migrates, ice lenses will form in that material. And that's what causes the heave, because this surface is now higher than the original surface was, because as the water freezes, it expands, and those lenses occupy space. And we have coming up a video from the Cold Regions Research Lab.
It's going. We can't hear the sound, Willie. You're going to have to narrate it.
What do I'm going to pause it. I think. Okay.
I can narrate it for you. I know it pretty well. If you
Okay,
want.
go for it.
So what you're seeing is a time-lapse photography of a freezing front. There was a white line there. There's a scale on the left. You can see it's going up because the soil is going up. And you can see the lovely high-tech timing device that they used to take the video so they could go back and do recordings later on. And each of those little black lines you see is actually a very, very thin, small lens of ice that's being formed by the water that's being pulled up into that particular soil. Okay, so that's what you're actually seeing is the freezing front growing throughout that soil sample. Now, this particular video, they had to move down to the bottom. It's a 8-inch high sample, so they moved their little high-tech timing device to the bottom. You can see the scale is still going up on the left. The test started at 19% water. It ended at 55% moisture content. So all that water is not the water that was there initially. It's the water that got pulled up by the capillarity, and the 8-inch sample heaved 4 inches, half the soil sample height. So that's I've seen that video just a few times there, Willie, as you can probably guess. And there's one that's more like what we see in the field. That's a 1-inch, 3/4 inch thick lens of ice, and then there's a 1/2-inch one above it. I've seen 3-inch thick lenses of ice. I don't know what you've seen, Willie, but digging them out in the winter when a culvert actually collapsed. And of course, that water has to drain away in the spring. And where's it going to go? Well, probably not where we want it to go. And it's certainly going to keep the road wet, especially if you have too much of the silt and the clay and stuff like that. And of course, everybody's favorite season, pothole season, comes into play. So, no, I didn't quite narrate it exactly, but what the heck. Okay, back to you.
Okay. So we get to the end of that, and we have the spring thaw. where the warm temperature and the thawing front is migrating down through the soil. And you still have this frozen layer below. So you then have soil with excess water content in it. And as we generally know, when you have soil with too much water in it, we often refer to that as mud. And living in Washington County, right near the border with Vermont, come March and April, the Vermonters refer to this time of year where everything's thawing as mud season. And because this is frozen below, the water can't go down. So you've just got this big squishy mess unless your soils and embankment are free draining and it can go out the side. Now here's a frost susceptibility group. Gravelly soils, you don't have to worry about them. In fact, in a lot of cases, we will either add fills or undercut and put gravel in if we've got areas with a big frost heave problem. Sands aren't so bad. Clays can be problematic. Fortunately, with clays, they don't have the permeability, so it doesn't draw a lot of water. And then silts, again, that's the Goldilocks, just right, just enough of the permeability and just enough of the capillarity to create all kinds of havoc for us. Okay, poll question. What's necessary for frost heave to occur? You can choose all that apply.
I expect this one may take them a little bit longer because we're making a multiple choice here.
You got multiple opportunities. You can choose freezing temperatures, heavy traffic, available water, frost susceptible soils, or excess salt from snow and ice control operations. Pick all that apply.
Got about half the people have voted.
Okay.
We'll give them another 15 seconds or so, see how many we get.
All right.
There you go.
Okay. Frost susceptible soils, 98%. Absolutely. Freezing temperatures, yes. Available water, yes. Heavy traffic will not cause frost heave. However, heavy traffic will create all kinds of havoc on your pavement during the spring melt and during mud season. And excess salt typically isn't a factor, although if it's thawing, if you've got cracked up pavement and it's migrating through and thawing the surface layer of soil, it could create some problems. Okay, we want to build our roads on a firm foundation. This was out in California after a water main break, but you got to have something you can drive on. Now, stability is how much bearing capacity we have. How much will that soil support? And it's all over, it's everywhere, depending on what you have for soils. And here's some bearing capacity indicators. Soft clay, 1.5 tons per square foot, which, you know, not too good. Stiff clay, 2.5, and, you know, it gets progressively larger, but keep these numbers in the back of your mind for a minute as we go to the next slide. You know, bedrock, 100 tons per square foot. It'll hold buildings up. Now, here's a unimproved road that has low soil stability. So the vehicle that drove on it rutted it up. And just as an indication, if you have a vehicle that's has auto tire pressures at 35 psi, that's 2.5 tons per square feet. Truck tires at 75 psi, that's 5.5 tons per square feet. And some trucks routinely run their tires up in excess of 100 psi, whether they're supposed to or not. But backing up, anything below this that doesn't have a pavement or surface on it is going to be a problem. So, how do we get strength in our subgrade soils? Well, we want to compact it. We want it so it's as compressed as it's going to be, so it's not going to compress while we put loads on it. And we want it to be nice and stable. So we use varying types of compaction equipment depending on the soils. We have steel wheel rollers here, which are good for pavements, gravels, sands. Rubber tired, usually we would use for chip seals and that type of thing. And then as we're into the silts and clays, we're probably going to be using a different piece of equipment like a sheep's foot roller to try and get those clays and silts compacted adequately. And if we try and run a steel wheel roller over clays, we tend to just push it around and make a mess. It's like pushing toothpaste around. So one of the things we want to take a look at on density is how much moisture do we need in those soils to get the maximum amount of density out of it. And we do that by running a proctored test. And basically a lab comes out, takes samples, and will compact the soil at varying degrees of moisture, plot the results in density, and you'll have the curve, which will indicate about what the optimum moisture content is. And then you'll want to add water or let your soil dry out till it's pretty close to the optimum density, and then compact it. I was actually out at a project site today, and we were doing density tests, and they were doing it with a nuke density gauge, and we weren't getting the densities we needed because the soil was just too dry, and the contractor was going to need to add water to it. So optimum moisture contents. In order to get your soil compacted to the maximum density, sand, 6 to 10%, but as the soils get finer, the optimum moisture density climbs up to 13 to 21% for clays. Okay, soil summary. Clays, silts, and we're going from fine particles to progressively larger ones. Silter clay mixes, and we're also going from what are less desirable to build our roads on to more desirable. Silter gravel with a few clay fines. Sander gravel with silt fines. And our favorite is clean sands and gravels. Now, this is, David was just a little bit younger when this photo was taken, but he's running a proctor test and trying to determine what the actual optimum density is, not pretending to be an expert and saying, yeah, this is what it is. So field soil identifications you can use is you can visually look at ballpark gradation. You can tell if it's sandy or gravelly because you can see those size particles. For plasticity, you can make it into a little snake or a ball if it's a fine grained soil and see if it'll hold together. You can see if it's draining, you know, if it tends to pond water or not. And the other thing you can do is if you pick it up in your hands, the clays will tend to give you that kind of fine sheen that gets all in between your fingerprints, which is one of the reasons they use clays in the paper making industry to make the nice, smooth, shiny paper that you get with magazines. So, lab tests you can do. Gradation. You dry it out, you run it through a bunch of sieves, and then you weigh up what you have left and see what you get, what was retained on each sieve and see what you got. You can do a proctor, which we saw the photo of earlier, where you compact several samples, determine density, and then dry them out. And then you can do a sand equivalent test, which you dilute it in water and with a flocculant, and then measure how much sand, because that will settle out first, how much silt and clay, and how much clear water you have left. And that will give you an idea of what your sand equivalent is. And for a base course, you want to be greater than 40. For subbase, greater than 35. And then for a gravel surface in the 25 to 40 range. So it's, again, we're trying to do things that give us the best opportunity for success and minimal maintenance problems. Now, a lot of us don't have the luxury of building roads on good soils. And there are a variety of approaches we can take, and we'll go over a few of those. We can just add material on top and build it up and have a nice big embankment. Sometimes that's not economical, sometimes we don't have the room, and sometimes the soil beneath is not stable enough to support that additional weight. But on some occasions it can work. One of the things I was told about adding material on top is one of the towns here in Washington County many, many years ago wanted to straighten one of their town roads and run it through a swamp. So on Monday morning, they came in and they just started hauling sand and gravel and creating an embankment into the swamp. And hauled all day and then went home for the night. And Tuesday morning they came in and all that material they had hauled in the day before was gone. It had sunk into the swamp. So Tuesday, they hauled material all day. And like, Tuesday night, they went home and came back in Wednesday morning and they had the same results. It sunk into the swamp. And after they did the same thing on Wednesday, came in Thursday morning and all their material was gone because the soils in the swamp were so unstable, they just abandoned the project. One of the other things we can do is undercut our roads, is we can dig out a certain amount of poor material and replace it with good material. We can blend good material with the existing material to improve the gradation. We can stabilize our soils. And I didn't mention calcium chloride, but that's another agent that's included along with cement and asphalt to give us more stable soils to build a road on. They do have their limitations, but in the right application can work well. And we also have geotextiles and geogrids. Geotextiles do two things. They separate the poor soils from the good soil above. So it keeps the clays from pumping, clays and silts from pumping or migrating up into your base and sub-base course and fouling them. It also provides some degree of reinforcement, and some of the woven geotextiles will provide a little bit of tensile strength, again, little bit, for when the pavement is loaded, as we saw in the earlier slide. Another strategy is geogrids or geocells. On the left, we have Geogrid, and it's just a big plastic grid that you roll out on the subgrade soil and place stone on top of it. And that geogrid provides a tensile reinforcement underneath the stone, and the stone locks into it. And quite frankly, if that town was doing the road on the swamp, a geogrid might have enabled them to cross it. Over here is a geocell, and those cells are laid out and filled with stone. This is actually in Warren County, New York, where there was a swamp, wet area with poor soil stability that was undercut, and they put the geotextile underneath, the geogrid on top, and filled it with stone and constructed the road on top of it. And the geogrid or geocell was actually a military application, so the military could quickly and effectively construct a runway to land planes on like beaches. Okay, base and sub-base material. You want granular material with angular particles. You want angular particles because if they're nice rounded particles, they act like ball bearings, and under load and traffic, they will start to move and will rut. We had that in Washington County. We had a pit that had granular sand or rounded sand, and it was a tough material for building roads, and we ended up with a lot of ruts on roads that were built with that. We want well graded with very few fines. We want low fines so our permeability is high, so water will drain out of it. We want it to be stable. We want to be able to drive on it and support the pavement above. And we want high permeability, which is, again, why we want low fines. And we don't want something that's plastic. We don't want it sticking together. And we don't want frost susceptibility, otherwise we'll be out there with frost heaves all winter, and then we'll have potholes in the spring. Okay, so here are the New York State DOT sub-base course specifications. Types 1, 3, and 4 are all bank run materials. Type 2 is crushed stone. The gradations on 40 and 200 are all the same, but the type 1 is a larger material. You know, 3-inch minus, and then the 2 and 4 are similar, although the 2 has less 1/4-inch stone. Okay, now we don't want to pave or put a hard surface on anything that won't support it, But once we get to that point and our subgrade and subbase will support it, there are a variety of materials that are used around the country, and in New York too. We've got asphalt, which seems to be pretty common for local roads and a lot of state roads. We've got Portland cement, which is not only used on high traffic roads like the Thruway and interstate highways in some of the western states, like Nebraska and Washington, they're in Colorado, their local streets are often Portland cement. We can have surface treated roads, which we had quite a few county and town roads in Washington County, which were a sound gravel road that was in pretty good shape, but the traffic was getting to the point where it needed a hard surface. So an asphalt and stone surface treatment was put on it. We have our gravel roads, and then in some of the older parts of the country, you may have brick or concrete pavers. This photo here is Ithaca, New York, with, I believe they're concrete pavers, not brick. I grew up in St. Petersburg, Florida, and the old section of the city that was developed in the 1920s was all brick streets. Okay, so as we're paving our roads, you know, we got our cut section, our fill section. We may need some geotextile to separate our bases, subbases, and embankments from our soils. You know, we've got our width of, 18 to 22 feet. But notice here, we got a 1/4 inch per foot of crown, both on the surface and then down below at the subgrade level. So if any moisture does get through here, ideally, it'll get out to the side in daylight. Now, time for a poll question. What properties make good base course material? Pick all that apply.
We're getting a few votes in there, Willie.
Okay.
About a quarter have voted so far.
All right. You know, you can choose from rounded particles, low fines, high stability, frost susceptibility, or high permeability.
Almost 2/3. We're getting there. And by the way, you were correct. That was pavers in the city of Ithaca.
Okay.
They're made to look like brick, though, but they're really pavers.
I'll have to get one of my high school classmates down in St. Pete to snap some brick street photos for me.
We have some brick ones here. I can get you some pictures. I even have a brick from one of the old streets.
I used to ride my bike on them, and it was they were loose. And as I'd ride my bike down the crown of the street, the bricks would rattle a little.
Okay, well, we're going to get started here just because we got about 10 minutes to go. So here's your answers.
Okay. High stability, definitely. Low fines, absolutely. High permeability, we want that. We want it to be free draining. Frost susceptibility, we typically don't want that because we don't want to have to deal with frost heaves or potholes. And then rounded particles, we don't want, and I can vouch for that with the Washington County experience because it just acts like ball bearings. Okay. So, other thing that we can use is cold mix asphalt concrete. You're just using aggregates, but you have to have good evaporation because it's an emulsion and you want it to evaporate and break. Otherwise, the stones will just come out of the loose material. Hot mix, which is what we commonly use. DOT has their spec. We want to put it down when it's nice and hot, 250 to 325. And if it gets below 185, it doesn't cool well. And if we're trying to compact it as it gets into the tender zone, which is often between 240 and 185, it will just push around and you'll have lines and creases in it, and you'll be chasing those around all afternoon until it cools down below 185 and you can get it out. And we use hot mix asphalt as, you know, base, binder, shim, surface, variety of things. Concrete pavements. Here's a residential neighborhood in Lincoln, Nebraska. Concrete street. Permeable pavements in Warren County and along Lake George. They put permeable pavement in, and it's open graded, and the water flows through the pavement. But in order to keep it functioning, you have to clean it on a regular basis. So there are maintenance issues, but it minimizes runoff. Now, if you recall in the earlier slide with the surface road, we had 1/4 of an inch per foot on the top and on the bottom and then on the top. Here with a gravel road, it's 3/4 of an inch per foot on the surface. And that's because gravel roads tend to become somewhat irregular over time, and we want enough pitch to get the water off the surface so it's not sitting there. And this is predicated on a 12-inch base course and then a 4-inch surface course, and it's not the same material. You want fewer fines in the base and a little bit more fines in the surface to hold it together. Okay, so aggregate road surface. You want granular materials and the 8 to 15% fines, and that little thin layer may be somewhat frost susceptible, but hopefully it's thin enough that it's not going to be a big factor, although it may thaw out during mud season. So, poll question: what methods can be used to mitigate or subgrade soils? Pick all that apply. Geotextiles, increase the traffic on it, stabilize the soil, eliminate the base course, or use geogrids.
They're coming in, Willie. We got about 40%.
Okay, good.
We got one person put it into the Q&A pod, but
that's been going all the way along.
They're getting the same answers as everybody else too. So that's good.
That's good.
Almost there. Stay on target. We'll give them another 5, 6 seconds here. We'll go ahead and show the results. There we go.
Okay. All right. We can use geotextiles. We can stabilize our soil. We can use geogrids. And there's always one. We probably don't want to eliminate the base and subbase. That will make it worse. So.
And a lot more expensive.
And a lot more expensive because you'll be using a lot of asphalt or fixing things frequently. So if anybody has any questions, you're welcome to put them into the Q&A pod. And otherwise,
we'll give them a minute. We got a couple of minutes.
We'll give everybody
has a question.
And I'll just throw up the shameless advertising. Well, waiting on any questions. Okay. Any experience with Pack? No, I have not had any experience with PosiPack, so I really couldn't tell you. David can probably answer if the presentation will be able to download.
We will be posting the video of the presentation. It'll be on our YouTube channel. People can download that or you can watch that online.
Great. I appreciate everybody's time and attention. I hope I didn't put anyone or didn't, reinforce the obvious.
So everybody who was on the webinar for at least 3/4 of the time, you'll get a certificate of attendance. And yes, for those engineers, once you get it, if you were here 90% of the time, you send us your certificate. We'll get you a PDH for that after you get your certificate, send it in to us. With that, thank you very much for joining us. Great job, Willie. And
Thank you.
Any last words there, Willie?
If you're building pavements, know what's underneath so you have a good handle on how to deal with it, because despite some beliefs to the contrary, one size does not fit all for pavement section.
Sounds good. Thanks very much, Willie. Everybody have a great day and stay well.
Thanks.